Okay, so all opinions expressed in this presentation are my own, don't necessarily represent those of my employer. I'd like to address this from more of a clinical and from a biological-based perspective rather than data analysis-based perspective. But what I'm interested in is, are there better ways to generate data on AMR and to analyze said data? So I'll talk about AMR, why it's important, how antibiotics work, combating AMR, the different types of AMR data, and if we have time, some methods for the measurement of AMR to kind of put it into context of how we actually measure antimicrobial resistance in the laboratory. So what is AMR? Why is it so important? I think you've probably seen some of these statistics already today. It's one of the top 10 global health threats according to the World Health Organization, responsible for many millions of deaths. Of the 1.27 million deaths directly attributable to AMR, this is in 2019, there was 1.27 million. When you put that into perspective, tuberculosis, the leading infectious disease, 1.5 million, HIV, AIDS, and malaria almost add up to the same amount as responsible for AMR. Even more worryingly is approximately 2/3 of the attributable deaths were caused by resistance to first-line antibiotics, i.e. first-choice antibiotics, the ones that your doctor would prescribe for you. So clearly AMR is associated with substantial disease and economic burden. Now, antimicrobial resistance has a definition problem. There appears to be two definitions. The lay definition, which basically bacteria, fungi, viruses, parasites change over time and no longer respond to the medicines. But that's not strictly accurate. AMR is the inherited ability of microorganisms to grow at higher concentrations of an antibiotic, and that causes antimicrobials used to treat the infection to become less effective, not necessarily not work, and it's very important, the genetic component of it. And contrary to popular opinion, resistance doesn't necessarily emerge from exposure to the antibiotic. It can emerge from exposure to the antibiotic, but in the vast majority of cases, it doesn't. So there are a number of other cases where the lack of effectiveness of antimicrobials is not due to AMR. There's tolerance. This is associated with treatment failure and relapse of infection, but it's the ability of an organism, whether inherited or not, to survive transient exposure to high concentrations of an antibiotic. This is often achieved by slowing down metabolic processes and confer advantage against several antibiotic classes, whereas resistance tends to only be a single antibiotic class. This is an example of tolerance. The antibiotic daptomycin is one of the first-line antibiotics used to treat MRSA infections. Methicillin-resistant Staph aureus is still one of the major pathogens there is. Staph aureus is a gram-positive organism, and daptomycin attacks the cell membrane here at the bottom. Gram-negative microorganisms also have a cell membrane. However, they're tolerant of daptomycin because they have an outer membrane. Daptomycin cannot penetrate the outer membrane. So that's the key difference. There's also persistence. This is the ability of a subpopulation of a supposedly clonal bacterial population to survive high exposure to an antibiotic. And this is non-heritable, it's not genetic. So in this example, you can see in almost every population of bacteria, approximately 2% of these will be persister cells. This can vary depending on infection, depending on the conditions, from anything from 0 to 20%. There's no genetic change in these cells that cause persistence. If you subculture them, re-expose them to the antibiotic, they'll be susceptible, apart from a persister subpopulation. Fortunately, we have an immune system. Killing off enough of the antibiotics allows our immune system to kill off the remainder. Persistence is poorly understood and is the subject of a lot of research at the moment. Finally, dormancy. This is often seen as an extreme form of tolerance. So most antimicrobials interfere with cellular metabolic processes. For example, fluoroquinolones interfere with DNA synthesis. If a cell's not metabolically active, the antimicrobial will be ineffective. Some antibiotics, however, don't rely on metabolically active cells. For example, polymyxins such as colistin disrupt the cell membrane, and therefore dormant cells are susceptible to these antibiotics. How antibiotics work, there's a variety of them. DNA replication, active metabolic process, same for RNA replication, protein biosynthesis, cell wall biosynthesis, and strangely, folic acid biosynthesis. We acquire folic acid from our diet, whereas bacteria have to synthesize it themselves. That's why it makes a target for an antibiotic. So cell membrane is a good target for an antibiotic because it can kill tolerant cells and dormant cells. However, unfortunately, there are only 2 membrane-active antibiotics in clinical use. Well, actually 3. There's 2 polymyxins and daptomycin. That's it. So they're a target of a lot of research, but not a lot of success. The resistance mechanisms, there's a lot of variety of different resistance mechanisms. Sometimes the bacteria doesn't even have to do anything. It just pumps the drug out faster than it can get in, or it can block the drug from getting into the cell. You can modify the antibiotic by inactivation. You can bypass the effect of the antibiotic by having an alternative protein that can function in place of the target of the antibiotic. So there's a number of different mechanisms of resistance as well. So combating antimicrobial resistance. This has to be a One Health approach, a global approach to combating AMR. Public awareness is vitally important for this, as is antimicrobial stewardship. Sanitation and hygiene are probably the most important thing and a huge problem in LMIC countries. Reducing use in farming and the environment will help against the problem, as will the use of vaccines and alternatives such as bacteriophage therapy, as we heard about earlier, and other things such as antimicrobial peptides. We need improved and rapid diagnostics. This cartoon here shows that normally antibiotics are given with an empirical diagnosis and can take a long time before you get to the right antibiotic, if you do at all. If you have a rapid diagnostic test, point of care test, you can get the right antibiotic at the right time, treat the patient much better, and limit the risks of resistance. Novel antimicrobials are obviously vitally important, but I would say that since I'm the head of the antimicrobials program at the BioAster, so I obviously think this is important. Where I think data science can really help us is improve global surveillance of AMR. The accuracy of global surveillance of AMR is sadly lacking, and I think partly this is because of reporting, but partly because of the tools that are used to carry out this surveillance. For example, reliable and accurate and representative information on the incidence of resistant infections is vital for monitoring the national and global scale and identifying emerging threats and evaluating the impact of interventions. The local level, this information would help improve patient health. National level, surveillance data can inform health policies and in response to health emergencies. And at the global level, it provide early warnings of emerging threats and help identify long-term trends. We have to remember that the vast majority of antimicrobials, and especially antibiotic prescriptions, are made outside the hospital, so without the use of a diagnostic tool, or often by pharmacists or for self-medicating patients buying antibiotics over the counter. So what causes AMR? Inappropriate prescribing, the overuse of antimicrobials or overextending the treatment duration. Conversely, not treating for long enough is equally a problem. Antibiotic overuse is a huge problem. Between 2000 and 2015, antibiotic use increased by 65% globally. This is a huge problem. This is predominantly due to increased use in LMIC countries. Obviously, the dissemination of AMR microorganisms is a huge problem, as is inadequate access to water, sanitation, and hygiene. Inadequate healthcare services are also a huge problem, with inadequate diagnostics and the lack of affordable and appropriate antimicrobials. Poor infection control measures. You know, when they tell you to wash your hands or use this gel when you go in the hospital, this is really, really important. And so the overuse of antimicrobials and the lack of antimicrobials seem contradictory, but do reflect the problems faced by developed and LMIC countries. So prospective AMR data, this is where we get all the horror stories that you read in the newspapers rather than the scientific journals. For example, by 2050, 10 million lives a year are at risk due to the rise of AMR. A cumulative $100 trillion of economic output are at risk. And by 2050, the death toll could be a staggering one person every 3 seconds. These are all based on the now famous O'Neill report that came out in 2017. These are all at risk. This might not happen, but it could happen if we don't do something very soon. So historical AMR data, this is where I'll talk about some data. However, I have a disclaimer before I talk about this. I'm not a mathematician, I'm not a statistician, I'm not a data scientist, I'm just a microbiologist. As far as my knowledge of statistics, data science and maths is concerned, it's the following. Reporting the standard error is much better than reporting the standard deviation because it makes your error bars smaller. I've gathered that large N numbers are better than small N numbers. And once you get beyond calculating the mean, I've got to be honest, I'm a bit lost. GraphPad prisms has saved my life on many, many occasions. I know what statistics need to be done, how you calculate them, not a clue. Therefore, we need the help of data scientists, statisticians, biostatisticians, people who can do AI, machine learning. We need, us biologists, we need help with this. So back to the historical AMR data. The best historical AMR data tends to come from point prevalence surveys. This data collection tool used to identify the number of people with a disease or condition at a specific point in time. These are vitally important sources of AMR information. However, they are still flawed. There's a very limited number of point prevalence surveys carried out in LMIC countries. They're often based on small sample sizes, which can introduce bias, limit the usefulness of findings. There's a recent global survey published in 2022 in The Lancet, probably the best paper there's ever been on the incidence of AMR and the problems associated with it. And they calculated that there were 136 million AMR infections between 2010 and 2020. This survey concluded data from 99 of 195 countries, so half, roughly. It contained only 11 LMIC countries that reported data. The World Bank defines what's an LMIC country, and the World Bank says there are 132 LMIC countries and only 11 reported data. This small map of the world is from that paper. The countries in white didn't report data at all. If we just take 3 of these countries, the USA, Brazil, China, that's roughly 25% of the population of the planet where there's no data available. This is not good. Also, extrapolating country-level infection rates and persistence prevalence from available but scarce data at the hospital level, where most point prevalence surveys are done, introduces uncertainties, assumptions, and can impact accuracy. Additionally, the lack of data can prevent the implementation of AMR policies on a countrywide level. The heterogeneity of data from different sources, differences in data collection methods, diagnostic criteria, reporting practices can all affect the reliability of estimates. This applies to the pathogens, the antibiotics, the sample types, and whether it's from community or hospital data. So what are the data challenges? There's unreliable data on infection, on AMR. There's difficulty in attributing burden specifically to AMR. For example, there's a statistic here, fact here. Patients with longer hospital stays are more likely to have AMR pathogens than those with shorter stays. Why is that? Is it that AMR causes these longer hospital stays? Or is it just that patients who stay longer in hospital happen to pick up drug-resistant infections? Let's face it, hospitals are full of sick people. How can we distinguish between patients who died of resistant pathogens or those who died with resistant pathogens? Just because you've got an AMR pathogen isolated from the person, that's not necessarily the infectious agent causing the disease. And it doesn't have to be the microbe that's there in the highest numbers. For example, E. coli 0157 can cause severe gastrointestinal disease. You have approximately 10 to the power 12 microbes per gram in your gut content. 100 E. coli 0157 can cause gastrointestinal disease. That's not a very large amount. I didn't calculate what it is, but it's 0.0000 something percent. So finally, I'd just like to show you a bit of evidence, a bit of information on how we actually measure AMR, how we measure antibiotic susceptibility or not. At the simplest level, we carry out what's called minimum inhibitory concentration determination. So this 96-well plate here has 4 different pathogens on it. The one in lane E and F is showing growth, whereas the ones in A to D and G to H show much limited growth. So this is showing resistant to the antibiotic in place. We can use more sophisticated techniques looking at changes in gene expression, transcriptomics, qPCR. You can plot these volcano plots about genes that are upregulated or downregulated by antibiotics exposure and resistance. You can also do changes in proteome production, Western blots at the simpler level or proteomics, and then you can do principal components analysis, look at the differences in the proteins and predict AMR that way. Bioaster, we're developing new techniques based on shotgun metabolomics, where you can see that certain key metabolites change in production on exposure to antibiotics, and the resistant organisms have a characteristic pattern different from the susceptible organisms. And so you can diagnose AMR, and this pathway takes it's about 8 hours compared to at least 24 hours for more conventional techniques. Even better is this technique, holomoa. This is based on digital inline holographic microscopy in combination with machine learning. So basically you take micrographs of multiple bacterial cells exposed to different antibiotics, and you generate a computer database of the effects. So you can see here that ampicillin is causing significant elongation of the cells relative to control cells. Amoxicillin causes bulging of the cells. Meropenem causes swelling of the cells. You can also look at intracellular features such as density, because you can cause condensation of the nuclear material as well. And within this, by using a convolutional recurrent neural network, you can define what class of antibiotic is the microbes are or are not susceptible to. And this can take about 3 hours. So we can speed up the diagnosis as well. So conclusions and future perspectives. I think we need to standardize the core infectious syndromes, pathogens, and antibiotic classes that are included in AMR surveillance. This would improve comparability between surveys within countries, between countries, and eventually at the global level. The World Health Organization proposes a 2-pronged approach, generating nationally representative data and also conducting periodic surveys to measure the prevalence and trends of AMR. Active AMR surveillance through periodic national AMR prevalence surveys does offer a reliable and direct measurement, but could be improved. There are other methods than point prevalence surveys, for example, sentinel systems or lot quality assurance sampling, which is a lot less data heavy, but has limitations in the amounts and sizes of samples captured. Finally, future prospects. How can the surveillance of AMR be more accurately monitored? Are there low-cost parameters that could be assessed that might increase the accuracy of AMR surveillance and also improve the number of people that contribute to these surveys to give us a truly global picture? Is it possible to coordinate these surveillance efforts to take into account human, animal, and the environmental sectors? Finally, is there a place for mathematical modeling in AMR surveillance, or artificial intelligence, or AMR surveillance, or machine learning? Finally, I would generally like to hear your input on these matters, because I think what we're lacking as biologists, as microbiologists, is input from data science. So please feel free to contact me whenever you like. Thank you.
Okay, thank you for a great talk. Of course, it was as on purpose. Should be different talk than on all the other talks, because I think we need also the additional perspective to understand how we really should look at the data, and what data are available, and what are the real challenges. So, are there any questions, David?
I was very impressed by this world map where you show where we get data from. And one thing I don't understand, why there's nothing from America. It's not exactly a low middle income country, right?
Exactly, yeah. You notice Canada was there as well. There were certain parameters within the study for the data had to be of a certain quality, and the data fell below the quality requirements of the survey, basically.
Okay,
and then in America, it's not very coordinated between states as well. That's one of the other problems.
Okay, and maybe it's a completely naive misunderstanding, but it seemed as if in Europe and other richer places there were more incidences of AMR reported than in others. Is this a classical of, if I look, I'll see it, and if I don't look, I won't see it? Or is it actually indeed true that in, say, in Africa and other areas where there's less economic development, that there is indeed less AMR?
It's a fine balancing act. There's less AMR because they have less access to antimicrobials, but in some cases there's more AMR because of the lack of sanitation and hygiene and the inappropriate use of what antimicrobials are available. We have first-line antimicrobials that tend to be very good, which have relatively low resistance rates in the developed world, whereas in the LMIC countries, they only have access to the much cheaper, generic, older antimicrobials to which there already exists more resistance.
Thank you very much for the very, very interesting talk. I see more and more that antimicrobial resistance is not only a biological issue, but more like a societal, economical. So I would like to know, what is your take, and where do we draw the line between is this a subject that should be studied by biologists or data scientists, and where do we move on and start talking about this with politicians and people that actually can change behavior in cities? Because I think it boils down to cities that have no access to sanitation, as you pointed out, and in some cities, for some countries, you may have antimicrobial resistance, but they have other bigger problems. So I wonder, what is your take? How social is this problem?
I think it's a very social problem. I think that's why people like the World Health Organization need to be involved, and the developed countries need to help support the efforts of the less developed countries to improve sanitation, because that would be one of the biggest things and one of the cheapest things, and all the other ways to combat AMR. But I think the sooner it becomes a genuine societal problem, then the more we will be able to influence policymakers, politicians, because it still has, even the World Health Organization can just make recommendations. It's only at the country level that they can actually implement these policies. People can say that most countries have an antimicrobial resistance action plan. Very few countries, or not that many countries, actually implement said action plan. And I think one of the biggest problems is financial support for this.
All right. Yeah. Thanks for the very nice talk. I have a computer scientist question, so sorry about that. So I would like to understand a little bit more about the task of global surveillance, right? So is this more about monitoring, let's say, the spread and distribution of existing AMR determinants, or is this also surveying, let's say, the evolution and whether new determinants come up and how they act essentially?
It's both. Partly it's a comparison. You do comparisons progressive of different point prevalence surveys over time, so you can see the evolution of resistance. And there's always people on fishing expeditions essentially looking for new antimicrobial resistance determinants. It's probably early to mid 2010s, they found the new Delhi beta-lactamase resistance gene, which confers resistance to penicillin type antibiotics. That was, funnily enough, first identified in New Delhi. And they were able to track that within a year to pretty much the entire globe. So sometimes it's individuals in their own research groups go looking for these genes. Sometimes it's the result of constant analysis of these different surveys. So it's a mixture of things.
And can you easily tell apart whether something essentially just popped up and then spread, or something just has been found but actually has been present everywhere but has not been found in the past?
It's difficult to do that from historical data. That's the problem. And tracking the evolution is difficult because of insufficient numbers of samples. But in theory, it could be done. I'm just not sure that there's enough will financially and politically to actually be able to track these things.
Right. Thank you.
More questions?
Maybe connecting to Andre's question here from someone who comes from the technical, from the data side. You said you'd like our input on how we can assess the threat. Well, the first thing that people coming from the analysis side will ask is, okay, what data can we work on? So we saw this survey, which you yourself said is difficult to interpret. What other data are you aware of in the domain, also from your own company, where you would expect that people with a data background could help?
I think like what has been the subject of this series, they're looking at the environmental factors and trying to correlate that, because I mean most of this data is based on clinical data, and it's actually bringing these data sets together, I think, would make a big difference if you could correlate the environmental data to the clinical data, because there's data on the use of antimicrobials in farming. Obviously, someone earlier mentioned pigs, and data that China's banned colistin in pigs, and colistin's a last resort antibiotic. You know, after colistin stops working, we've got nothing else at the moment, and it's been used to as a growth promoter in pigs. I mean, it's not clever. Yeah. So, I mean, being able to marry these sorts of three data sets would be really useful. And I don't know how to do that.
Last question.
Thank you for the talk. I have a question about, you showed that you guys used the deep learning based on the images and it shows that somehow you can detect the AMR in quite a short time with this. Does the company also kind of work based on, because it is also known that genotype to phenotype relationships are also quite useful to detect the AMR. So does the company also work in that direction, like kind of building models where you can mine the genotypes and based on this you can detect the presence of AMR or something like this?
2 points there. We have a huge omics team. We do genomics, proteomics, metabolomics, lipidomics, you name it, we do omics, and we apply it to AMR as well. Second point, we're not a company. We're a not-for-profit organization. Any money that we make, we reinvest into the business to keep at the cutting edge of the technology. So we don't make money.
And what?
We spend lots.
And yeah, maybe I will talk later about this.